Hey, what's up YouTube? Alright, so we're back here, HVAC optimal start, day 25, which is exactly halfway. So we're still on model 3 from the P&L paper, which I highly suggest giving it a read. So let's check out model 3, day 25. Just like a little recap from yesterday, we were still had this code right here where we were comparing the results from scikit-learn and then just using raw NumPy underneath, which I bet scikit-learn uses under the hood, but there's actually probably a lot more going on when you use this library. There's probably some more significant like data checks, and it's a big library for machine learning, pretty popular in Python world. But when we, oh shoot, wrong script. Hold up. When we run this, we do Python math lesson script. We got the same results. Yeah, just a little bit of that lag there, but this was our alpha A, alpha B, alpha D parameters. And then like when we look at the, maybe I'll just duplicate this. And then if we drill into the paper, if you would start scrolling into resistance capacitance model, model 3. So here we are. So here's our alpha A, our delta temperature from set point, and the zone temp, alpha B and alpha D. So this is some of the things used to calculate alpha B, which I think we'll get into. And then they boil it down here, but this is kind of where we're at, where we're just kind of looking at how to calculate this stuff for our math models and predicting how many minutes it takes to warm up or cool down the building before people get there. Okay, so here's our mini example, and I guess they are giving us, let's see, what is introduction to matrices for technicians. I told AI when it was creating this work to make it easy enough for technicians to understand. That's kind of my background. Not the high level upper graduate PhD engineer. I think everyone should be kind of understanding this, at least from a high level. So hopefully these YouTube videos aim to making this not such a mystery or black box. You know, there's actually concepts anyone can understand. Okay, so let's get started. A matrix is a simple grid of numbers. In regression, we stack our input vectors into matrix X and our outputs into a column vector Y. The normal equation, X times X, I think, and Y computes the least squares coefficient. You don't need to memorize the algebra. It's more important to recognize what the shapes mean. Modern languages like Python or MATLAB perform these operations with built-in functions. Okay, apply these examples. So this is our little mini lesson for today. Debating if it's worth just deleting that, I guess. Looks like there's some problem with the way the code was formatted. Weird. I didn't even notice that till now, but I think we can fix that. For some reason, the way that AI, when it created the lesson, it looks like it had some issues. Well, this is kind of interesting. I've actually never done this before. I've done a lot of Python programming, not so much in matrix and vectors and linear algebra. I've actually never used this at operator before. Learn something new every day. So, okay, so this is a NumPy array. If you guys remember, Python doesn't really have a true array. It has like basic lists, like that is a list data structure, and which can be like an array in other coding languages, but Python is just a scripting language, I guess, and to do like a real array like that would be like compatible to like C++, Rust, or Java, you have to use NumPy. So this, I guess, is just taking the product of it, which is kind of interesting. So when we multiply these two together, we get a product of 39. I'm kind of might have to sit and think about this a little bit, how it computes that number. I suppose we could even ask, I swear, like ChatGPT for me is running so slow, but I could just do explain this. See what Google AI mode does. Yeah, why not? Python demonstrates matrix multiplication, defining matrix A, matrix B. So this is a 2 by 1, and this is a 2 by 2 matrix, or defining vector, matrix A and vector. The at symbol is the NumPy operator for matrix multiplication, dot product style. Okay, so this is what I was looking for. Cool. So this 1 by 5, so we like multiply this number by this number, this number by this number, and you add that together, 17, and then the bottom element is this number times this number, this number times this number. So, and then I guess you okay, it's been so long since I've done any of this, so when you do the resulting code here, kind of interesting, I guess. So I'm just kind of curious to put this in its own line. Oh, okay. So I don't know. I guess this is just the demonstration of matrix multiplication, which I don't think we have to. I'm not going to dive too deep into, even though I probably should take some more refresher courses on linear algebra and matrix multiplication. I know the computer's constantly crunching this stuff. So it's just to kind of maybe show that, like, under the hood in Model 3, you know, where we're fitting all these coefficients and doing linear regression, that there is, you know, this stuff going on. So a lot of complex stuff. Maybe I should just show you guys this right now. So we'll probably show you this at the end, but like Model 3, when it computes, it's like computing this like 3D plane. So this is kind of like where all this comes into play. even though these ideas are kind of wild. So we're kind of fitting this plane right here. So that's why it's, complex multiple regression, matrix, algebra. It's, we can just look at it from, it's doing this stuff. And, like have a good grasp on delta t, our weather factor ratio, and our minutes to set point, which the computer science patterns capture. When we start up the HVAC, we capture how many minutes it takes to warm up the zone. And then we're kind of using all of this matrix algebra, linear algebra, matrix multiplication, whatever, to do this stuff in the middle. So maybe we'll get a little bit more into that, but I think that's it for this video. I might actually update the tutorial to be, this actually explains it, I think, a little bit better, as here it was a little bit vague. Create two 2x2 matrices and compute their 2x2. Why do you use matrix multiplication to do? How does adding a column to one of these change? I actually can't remember how to do this, so maybe I'll just let's just see what this says. I think like people could create like a whole like college, you take a whole college course in this. So okay, so that's just saying that we could create a 2x2. This could be like that, and then these are the same size. So, oh shoot, sorry, wrong code again. Math plus script. So okay, so we did that with two matrices the same size. Okay, the second question. In linear regression, we aim to solve the equation y equals xb because x is usually not a square matrix. There are more observations and features. We cannot simply invert b. Instead, we have to use normal equations. So it's getting a little bit into this, adding the columns of one thing again. So it ensures the regression line is not forcing the path through 0, 0, which we talked about yesterday. So okay, so I think that might actually kind of sum it up. This gets a little deeper into the math than I thought we would be. I think this is way harder than for technicians to understand, but the idea is to just maybe introduce it in this will just be, just know that there's kind of complex stuff going under the hood. So that's why in the Java program object, in the Niagara framework, like we're not doing any of this. Like it's this is too complicated, unless there was some math libraries to use. Let's see what day 26 is. So it looks like okay, so next I think we get into just one of these self-tuning algorithms run. They're like self-tuning algebra equation, whatever you want to call it. I think we get into tuning the models and updating coefficients. So maybe we'll do these two tomorrow, and then I think that this actually maybe we could do all these tomorrow, and that'll sum it up for model 3, and then we have a week on model 4 from the P&L paper. that's it for today, guys. So thanks for watching. Talk to you guys tomorrow.